All right, next we're going to be learning about infinite sums. And I mentioned in the other video about what an infinite sum is. Like if we keep adding numbers in a list forever and ever and ever and ever, and you might feel like, well, wouldn't the answer just be infinity? The sum would just be getting bigger and bigger and bigger and bigger. And it's not always true. In some instances, you can find an infinite sum, and we're going to learn that today. Just so you know, on your formula sheet, we learned our explicit formula for arithmetic and our sum formula for arithmetic. We learned our explicit formula for geometric. This is the sum formula for geometric finite. We're actually just going to skip this, and today we're going to be learning this last formula, and this is the infinite formula. So if you want to write that on your formula sheet, this is the infinite sum formula for geometric, okay? All right, but before we get into that formula, let's just kind of go through these notes. Generate the first 6 terms of this geometric pattern. And the reason why I know it's geometric is because I have an exponent. Geometric looks exponential. So I've got 1/3 to the 1 for the first term, which is just 1/3 or 0.3 repeating. It says round each term to the nearest hundredth, so I could have made that, here, let's do 10th hundredths, 0.33. All right, and the next term, I'm going to just second enter that and make that a 2.11. And the next term, make that a 3.04. And the next term, make that a 4.01. And the next term, make that a 5.00. And the next term, make that a 6.00. And you'll notice with that rounding that eventually these numbers are becoming, in essence, 0. Okay, it's not technically 0, but it's really, really, really close to 0. It's 0.00137. And if I were to keep going, they're getting, like, I'm now getting scientific notation. It's now 0.000457. And they're getting smaller and smaller and smaller and smaller. So what is happening to the terms as you keep going? They are getting smaller. In fact, they are becoming basically 0. And what happens when we add 0? They are becoming basically 0. What happens when you start adding 0 to a number? Doesn't do anything, okay? So are they approaching some value? Yes, 0. So that's why we can do what we call an infinite sum, because the numbers you're adding on at the end is so minute, it's not really adding anything into the sum. All right, next example, generate the first 6 terms. Once again, this is geometric, with multiplying by 3 each time. This one we were multiplying by 1/3. These were getting 1/3 smaller. So 3 to the 1 is 3, 3 squared is 9, 3 cubed is 27. You can do those in your calculator if you don't know them. 3 to the 1, 3 squared, 3 cubed. 3 to the 4th is 81. 3 to the 5th is 243. 3 to the 6th is 729. Okay, so those are the first 6 terms. And now we're getting bigger, okay? They're getting bigger. Are the terms themselves approaching some value? I guess you could say they're approaching infinity. They're getting bigger and bigger and bigger. And so if the terms are getting bigger and bigger, then the sum will get bigger and bigger and bigger and bigger as you keep going. And in that context, we say you can't find that sum. It's just getting bigger and bigger and bigger and bigger. Okay? So now let's talk about when can you do an infinite sum, all right? When you continue to add the numbers in a list forever, that's an infinite sum. So you just keep adding and adding and adding forever. How does that even work? Well, there's only one type of infinite sum that is actually able to be calculated. And it's this scenario here, where the terms are basically becoming 0. And what that scenario is one, it's geometric. It must be geometric. And 2, the absolute value of r is less than 1. If the absolute value of r is less than 1, then you can calculate an infinite sum, because that means the numbers are getting smaller and eventually they're becoming closer and closer to zero. And so you're just basically not adding anything anymore. In this case, the sum is said to converge. That's a vocabulary word. That is when the terms are becoming closer and closer to zero, so the sum basically is becoming some value. This term means the terms are getting smaller and smaller, and therefore the sum of the terms is approaching some value. Diverge is the word to describe an infinite sum that does not have a sum, like this one. So this would converge because the numbers are all getting smaller and smaller and smaller, so you can just add them together. This diverges because the numbers are getting bigger and bigger and bigger, and therefore the sum is getting bigger and bigger and bigger. So if you can find the sum, the formula is equal to a sub 1 over 1 minus r. But you can only use this formula when it's geometric and the absolute value of r is less than 1. Notice there's no n in this formula, and that's because it's infinite. There is no final number. So one more little note here. An infinite sum converges if and only if the pattern is geometric and the common ratio is less than 1. Okay, so real fast, I'm just going to do one or two of these with you. First of all, the question is, do the sums converge or diverge? So the first thing you need to decide, number one, is are they infinite sums? And I just want to show you there's two ways to tell that these are infinite sums. One, they have the dot, dot, dot. The dot, dot, dot means they go on forever. And the other way is by the infinity symbol. These are two ways to tell that these are all infinite sums. So one, in order for the sum to converge, one, it must be geometric, and two, the absolute value of r must be less than 1. So like for this first example, 1, is it geometric? Because there's something I can multiply 200 by to get 20. So I can go to my calculator, I can do 20 divided by 200, I get 0.1. Pattern continues, so 200 times 0.1 is 20, times 0.1 is 2, times 0.1 is 1/5. If you don't know that, you can do math fraction in there. So yes, that is the pattern. R is equal to 0.1. So yes, it's geometric. And R is 0.1 less than 1? Yes, it is. So this sum converges. And if it converges, what does it converge to? What is the sum if you start adding up those numbers? And that's where you can use your formula. The infinite sum is just the first term over 1 minus r. 1 minus r. In your calculator, you definitely need parentheses around that denominator. And the answer is 222.2 repeating. And if you don't believe me, just start adding those numbers up. They're not going to give you exactly 222.2, but you'll notice that they're not far off. Just right there, we're at 222. Then you add the 1/5, which was 0.2, and we're getting closer and closer to this. The next number you would add in would be even smaller and even smaller and even smaller. So it's just getting closer and closer and closer to that number. All right, the next example that I'm going to do with you is, actually, let's skip down and do, say, number 6. So this is an infinite sum. This is definitely geometric. The reason why is because it looks exponential. The n is in the exponent, okay? So it's geometric, and then this is r right here. R equals negative 0.2, and the absolute value of negative 0.2 is plain old 0.2, which is less than 1. So this sum converges for sure. And the formula is to do the first term over 1 minus r. Now the trick is, what's the first term? Remember when we learned about sigma, that number is the position of the first term. I know it's not when n is 1, but this is where we start our sum. So the first thing we need to do is plug in 5, okay, to get this number up here. So 100 times negative 0.2 to the 5 minus 5. If you don't know that answer, you type it in your calculator using parentheses around that exponent or just putting in a 0, and it turns out to just be 100. And the denominator is 1 minus negative 0.2 because r is negative, like that. And that's the sum, the infinite sum. If you wanted to, you could generate the list of numbers to check your math, but they will add to this number, even if you keep adding forever and ever and ever, because eventually the numbers are getting smaller and smaller and smaller and you're not really adding anything.